299,792,458 meters per second. Nothing travels faster than light, right? To find out, I have with me astrophysics professor Robert Nemiroff from Michigan Tech University. Thank you so much for helping me answer this question. How are you?
Thanks for having me on your show. It's a pleasure.
All right. So you've done quite a bit of work on gamma rays, right? Gamma ray bursts, and you've done some work on faster than light travel. Is that correct?
Yes. So my research is involving things called gamma ray bursts, which are flashes of gamma radiation from across the universe. But also, over the past 10 years or so, one of my main focuses is on things that appear to go faster than light, because many physicists just keep repeating, many people keep repeating the phrase, nothing can go faster than light. And I used to sort of believe that, but then I came into some counterexamples that were really, really interesting. And so I started studying them. And I've been happy to do that for the past 10 years. Now I have graduate students working with me on some of these things and publishing papers on it. And it was an unexpected research direction, just trying to answer a question in my mind. Like, you're a very curious guy, I can tell from our previous conversation. So I have questions like you do. And I sometimes sit there and try to figure them out. And usually the answer is, everybody knew, it's kind of boring. But the answer to some of the faster than light stuff was not boring, and was generally, some of it was not known. So it was cool to work on it and to continue to publish papers on it, and a book on it too.
Yeah, you wrote a book called Faster Than Light, How Your Shadow Can Do It, But You Can't. Okay.
Correct.
So my shadow can travel faster than light. Is that correct? Yes, no, maybe? It can.
That is correct.
Okay. So how is that possible? Let's say, for example, you shine a flashlight in front of me. Let's say there's a shadow behind me. And then you turn off the light.
Mm-hmm.
What would happen? Like, would my shadow disappear faster than the light? Is that a correct way of thinking about it?
It's the movement. No. So if you turn off the light, what would happen is nothing for a while, because the light that was emitted before continues to move to the board behind you. So it doesn't know, the board behind you doesn't know. So your shadow continues to appear there. But finally, when none of the light from the flashlight reaches the background board, then it's complete shadow or complete darkness. Your shadow disappears because there is no light there. And that in itself is not a demonstration of faster than light things. By the way, many people don't know, even physicists don't know, that shadows can travel faster than light. It is mentioned in some popular physics books and even textbooks. But if you were to go into a university and go up to the physics department and stop somebody in the hallway and say, did you know shadows can go faster than light? Probably they would say, oh, no, they can't. But they can. We've published on that, and publications are reviewed by peers, and they can. So I think people who think about it deeply realize that they can, but it's surprising even to physicists.
So if you can come up with an analogy to explain how can my shadow travel faster than light, like, can you think of something like that? How would that work?
So let's say you take the, let's say you have a flashlight, and then you put your hand in front of a flashlight, and then you have a wall. So let's say you have flashlight, hand, and there's a wall up past the screen here. So yeah, so in a short amount of time, the photons from the flashlight will go through your fingers and cast a shadow on the wall. So you'll see the circle of the flashlight, but you'll see your hand blocking it out. So now the key thing is, let's start moving your hand a little bit. So you will see the shadow on the wall move with your hand. If the wall is really close to your hand, then you'll see it immediately. But now let's move that wall way back. So when you move your hand, it takes a while for the light to go from your hand to the wall. So it will take a while for the information that your hand is moving to reach the wall. But once it does reach the wall, then you have this angular blossoming of the light. So your hand becomes really, really large. And then it scales up completely. So when you move your hand, your super large hand moves at, if it's twice as far as your hand, if the wall is twice the distance from the flashlight as your hand, it'll move twice as fast. And you move the wall 100 times further out, it moves 100 times as fast. Your shadow of your hand is 100 times as large. But there's no limit. You keep moving it back. It takes a long time. You have to wait for the light to get to the wall. But when it does, the motion of your hand is translated at unlimited speeds. It can go faster than light.
So let me try and understand this correctly. So if you flash a light and I'm in front of the light, and first of all, my shadow needs to get to the wall. And then if I move my hand, the shadow is going to change faster than light at that point. But the shadow needs to form first. Is that correct?
Yes, the shadow has to form first. Your hand cannot go faster than light, according to most
The shadow
conventional
of my
science,
hand.
which I
Sorry.
believe. But but the shadow way back, if your hand moves, so for instance, you can use the moon. So if you were to take the flashlight and you take your hand and you take the moon's really far away. It takes light more than a second to reach the moon. So now the moon's up there. We go like this. If you could see your shadow on the moon, it would be moving faster than light. So you can move your hand
Interesting.
in front of the moon, away from the moon, in front of the moon, away from the moon. And that would happen after a second or so when the light left the moon. But then the shadow of your hand covering the moon and not covering the moon, that would change so fast that the shadow would move across the moon faster than light. The problem is that it's so dim that we can't see that.
So
But
you'd
it
need like
must
a very
happen
strong light
because
source.
you need a very strong light source. So here's a relevant example too. So let's say I have a laser pointer. So a laser pointer, yeah, or a laser beam of some kind. So now let's say that you have a dome that's 1 light year away. Okay, big dome. You just bought it. We bought it on Amazon. It's great. So, but it's huge. It's 1 light year away. So now you take your laser pointer and you point it at the edge of the dome. Okay, you have to wait a year for that red spot to go. It can be a green spot nowadays, all the way to the dome. Okay, but then what happens is you go like that. You move your laser pointer from one side of the dome to the other, right? So after the year it takes for light to go there, you could see the laser spot on the dome go from one side to the other. If you moved this in just a second, like I did, takes about a second to do that, you would see the laser spot on the 1 light year away dome go from one side to the other in a second. But the dome, we said, was a light year away. Therefore, the spot on the dome is moving much faster than light. So that's sort of like an anti-shadow. And that I deal with that a lot too. So people can see laser spots, so it's also very clear and very bright. So yeah, you can have two laser spots and say the shadow is in between. You can have a laser spot, then you can put a little of your finger between them, and the same thing would happen as it went across the dome. So the further out the dome is, the faster that spot moves. Yet no information, I would say, is moving faster than light because the information all starts with you and the laser pointer and at the hand that's creating the shadow. So the information goes from the hand to the wall, from the laser pointer to the dome. The fact that it goes across the dome does not mean that information is being transmitted from you to the dome faster than light. And although you can see the spot move across the dome, the information that is moving does not created on the dome. It's created
Interesting.
in your hand.
So
Therefore, if you're one spot on the dome and you want to communicate with another spot on the dome, you can't by pointing a flashlight or a laser pointer because that information always moves at speed. So you can have things. You consider the laser spot and the shadow to be the interpolation of unrelated events. Things go on, things go off, things go on, things go off. So the laser spot hits different points, but there's nothing really connecting them other than your eye thinking that they're connected.
So this actually got me thinking. Like,
Mhm.
if I am in Proxima Centauri, for example, you
Yeah,
know, it's like four light years away, and
a
you
great
know,
place to go.
we yes, it's on TripAdvisor, and you have a very powerful light source that has already formed a shadow in Proxima Centauri. Let's say you're standing in front of the show, and you want to communicate with me. So
Mhm.
you raise your hand to say yes, and then, for example, you lower your hand to say no, your shadow is going to change from my point of view. So, am I not? Aren't you communicating with me faster than light in that case?
Yes, the shadow will change. No, it doesn't change faster than light because the light goes from your hand, and the lack of light goes from your hand to Proxima Centauri only at the speed of light. So if I move my hand, you're not going to know about it for the 4 years it takes for light to go from here to Proxima Centauri. So you're not, but then suddenly you'll see some stuff. But still, you didn't learn anything. I can't tell you anything faster than light. It leaves my hand, it leaves my mouth only and goes toward you on Proxima Centauri only at light's speed, not faster.
Okay, interesting.
And
Um,
still, the shadows can go faster than light. They're both right.
but shadows are not really like they're abstract objects, like they're the lack of something, right? They're
Yes,
not like they don't. It's it's the non-existence of something physical. If that makes sense. That's
it's
what
the lack of
allows
light.
him to does that.
It's the lack of light. But a laser pointer is the actual light. So it's sort of laser pointer you consider to be an inverse shadow. And when you have your hand, you not only see the shadows between the shadows of your fingers, but the light that goes between there, that's real light. And that light is going from your hand to Proxima Centauri in this case. So
Interesting. Um, so I have another question regarding like the maximum speed two objects can travel away or
yes,
towards each other.
yeah,
Okay. Let's say, for example, I'm in a spaceship and you're in a spaceship,
yeah,
and we're moving at 99 C.
cool.
Let's say we both left Earth,
Yes.
both traveling at 99 C
Hell with Earth.
in the
Yes,
opposite direction.
yes.
What would someone on Earth see? Wouldn't they see like us moving twice at like almost twice the speed of light?
Yes. So if you're in a spaceship and you have mass, and I'm in a spaceship and I have mass, someone on Earth and we're going in opposite directions would say, "Oh, you're separating at close to 2 times the speed of light." And if we're headed toward each other, then they'd say, "Oh, you're approaching each other at close to the speed of light." But the key for special relativity is, and what Einstein said is, neither spaceship can pass you. Nothing can ever pass you faster than light. But you can consider other things with mass moving away as fast as twice the speed of light, and without mass like shadows, unlimited.
Okay. So what if we're approaching each other, right? We wouldn't see each other approaching at 2 times the speed of light. Would be slightly below the speed of light because of time dilation, I believe, and
Yes, yes.
length contraction and all of
Well,
that. And
there's
let's say,
yes, there's things called Doppler
please
effects
elaborate.
that would dominate. Well, if you actually look from one spacecraft to the other, things like Doppler effects dominate. But if you want to sort of forget about that for now, yeah. So when we pass each other, we'll say that was fast. That was really close to the speed of light, but not more.
So let's say, for example, we turn on our headlights. Like, I'm
Yeah.
curious, like, what would can I even see you? Like, what would I see outside my spaceship? Would you even look like a spaceship? What am I seeing?
So you would
Can you
see, yeah, the
imagine?
light. You would see the light that I would admit. I mean, it would be blue shifted because again, this Doppler effect. So you would see if I turned on a flashlight and you're in your spaceship, you'd see, yeah, you turned on the light, and the light you would see hit you, and then very soon after, you would see my spacecraft pass you. And with your light, you're signaling back. I would see the same thing. You say, "Oh, I see," and it would also be blue shifted. "Oh, I see that response, and that's very blue." And then zoom, your spaceship would the light I would see reaching me at sea, and I would see you zip by me very close to sea. So we would both sort of see the same thing. We would see blue Doppler shifted light, blue shifted light, and then the spacecraft passed each other right away. But neither the light nor the spacecraft we would record moving faster than light.
Okay. Now, I'd like you to clear some misunderstanding. Maybe my information is wrong or something like that. But I heard that you can accelerate indefinitely. Like the
True.
laws of physics allow you to accelerate forever, assuming you have enough fuel,
Yes.
right?
True.
So for acceleration, you measure it with like per second. So every second you're moving faster by an amount. For example,
Press that
10 meters
accelerator.
per second per second.
Put the
Yeah, we press the
accelerator to the floor,
accelerator.
right to the floor. Keep
Right.
it there.
Yeah, eventually, like for accelerating at the let's say gravity of Earth, even in like 30,000 seconds or something, I'm not sure of the math right now. That would mean eventually I've passed the speed of light.
Well, it
What is
sounds
going on?
reasonable, but that's not the way special relativity and the universe that we know work. So when you step on the accelerator, let's say you were to make a big loop. So yeah, when you come by, then I see, oh, you're moving pretty fast. And you keep the accelerator on, you go around again, you come back, oh, you're going even closer to the speed of light. You're going really fast. And then you do another loop and you come by and say, well, wow, you're even moving closer to the speed of light when you pass me. Yet you're thinking, oh, I must not be feeling the acceleration because I'm going only closer to the speed of light a little bit and not full acceleration. But that's not true. You feel the exact same acceleration all the time. You're zipping around. You're feeling the acceleration. If the acceleration gave you the feeling of gravity, it's like, oh, that's good. That's 1g. That's the normal gravity I experience. That's great. You would keep feeling that every time around. But yet I would never see you go faster than light. I would only see you get closer and closer and closer to it.
Would you get who gets older here? How does time dilation works in this case? Am I the one getting older, or are you the one who's going to get older? Do we know
Well,
about
it's a
that?
little bit like so the movie The Planet of the Apes, which I'm older, so I like the original one. I'm really most used to the original one. It has the right sort of idea there. So the spaceship that goes out and comes back finds an older reality. So in the Planet of the Apes movies, the Earth had evolved, and instead of having humans everywhere, there were apes everywhere. So but the humans on the spaceship came back and they were only just a little bit older. So if you were the one on the spaceship experiencing the change in the acceleration, you would come back and you would see me being much older. You could visit my grave or something like that. And you can say, wow, when we started this interview, you were much younger. What happened? But you would say, I'm pretty
uh,
much the same.
no, maybe we'll figure out mind uploading tech or something. Don't sell yourself short or something. Maybe it's still possible to speak. Um, so
Maybe.
I, I know quantum entanglement. You're an astrophysicist, but maybe you know about this quantum
A
entanglement.
little bit.
Like you
Mhm.
keep seeing these headlines that you can use quantum entanglement to communicate information faster than the speed of light. Are you aware of anything that might make that a remote possibility?
I'm aware of it, but the standard line is that you can't communicate faster than light. It is really, really strange, though. Okay, so let's say that um, you're on Proxima Centauri, and here I am on Earth, and midway between us, there's someone creating entangled particles, and you get one particle, and I get the other one. So can we communicate? So the person in the middle, if these particles go near light speed, let's say they move at light speed, it could even be photons, we can say, okay, then the person in the middle between us creating particles can communicate with each of us at light speed. That's not a big deal. But can I communicate with you? And the answer to that is no. What happens is we each measure something about our particles. They can be spin up, spin down. You can measure your spin up, spin down. But when we measure these particles, they seem to be random. Like, ooh, sometimes it's up, sometimes it's down. I don't know the pattern. And that's what I measure. And then you on Proxima Centauri, you're measuring, well, sometimes it's up, sometimes it's down. I don't really see a pattern. So if he's trying to tell me something from Earth, I don't know what that is. But then what happens is I can send you a signal and say, okay, and you have to wait the 4 years light takes to get from Earth to Proxima Centauri. And you see, it's like the answer key. You say, oh, when you did this and mine was that, I could see there's a correlation that when yours was up, mine was up part of the time. When yours was up, mine was down part of the time. So now I can see what it is that you were trying to say. But each time, all I see is random and all you see is random. But let's say, okay, now that we know what the answer key is, let's try it again. But even that doesn't work because the inherent randomness is embedded in it. It's only a statistical thing. So I can't promise you that your particle is going, if my particle is spin up, that your particle is going to be spin down. Your particle is going to be 50% spin up, spin down. It's the correlation later that appears to show that when I measure something, it seems to affect what you measure. And that information seems to go from me to you, or the other way, from you to me, faster than light. But it can't be used for communication because both of us just see random ups and downs. It's just random stuff. And that is really, really strange. But that is why people say there seems to be communication between particles faster than light, but you can't use it to actually send signals. Can't do it.
So it's like I'm sending you an encrypted message. You just
Yeah,
get some jumbled up mess, some useless information.
exactly.
Useless information that travels faster than light, but the key has to travel at maximum the speed
If
of light.
I transfer it from useless to useful, I have to get the key, and the key has to come from you, and it can only go at the speed of light.
Interesting. Now, for the speed of light, from what I know, is it's not just about light. Like that's like a
Yes,
maximum speed limit. Is that correct for
that's
anything?
correct. The
Um,
speed of light we used to be way back what the actual speed of light was, but now in modern science, modern physics and astrophysics, we really know it's like an abstract concept, which means it's the fastest that something can go. And light, for instance, if you put light through water, it's not going at the speed of light in vacuum. So the fastest that we know that anything can go is the speed of light in pure vacuum. Um, so we actually can measure that, but then again, we can only make approximations to it because we never really get to absolutely pure vacuum. But we can extrapolate and say, okay, we know what that would be. But the actual light probably doesn't go that fast. Other things move really fast too. Neutrinos move fast. Gravitational radiation moves fast. But all of them, the fastest they can go, the fastest anything can go, is approaches the speed of light in vacuum. Usually just said speed of light because saying speed of light in vacuum is too many words. But and not only that, but speed of light is not speed of light in vacuum just means maximum speed limit that special relativity uses in its calculations, and we think is the fastest that anything with mass can go. That's a real long phrase. Many so
um,
so we just use speed of light for that.
so, do we know why even is there a maximum speed limit? Um, has it ever changed, or has it always been constant? Do we know anything about that?
We don't know why there's a maximum speed limit. It took everyone by surprise. A little more than 120, 25, 125 years ago or so. So it is a surprise that there is a maximum speed limit. You cannot derive this maximum speed limit from any physics. It's usually considered to be a postulate. So here we are. There's some things we know. There's a lot we don't know. One of the things we know is that the maximum speed seems to be this. So we get it from experiments because nothing seems to go faster than that. Nothing with mass goes faster than that. And then we use it. Einstein famously used it to create special relativity, and special relativity keeps being confirmed again and again and again whenever it makes predictions.
You mentioned earlier how water can slow down light.
It
Like, how
can.
much are we talking about? Like, if I
Oh,
have like a flashlight, I have my diving suit, I'm in the water, I have a flashlight, and you're outside. You
mhm.
also have a flashlight. How much are you gonna win by?
So usually the light slows down in water. It's considered to be about 75%. Light speed of water is 75% of the speed of light in vacuum, and air doesn't slow it down very much. So we'll consider air to be vacuum for this segment. So yeah, so my light through air would go 33% faster than your light through water. But it's actually, you can get into lots of levels on this. So there's something called the front velocity of light. So even the front velocity of light is always the speed of light in vacuum, everywhere, even in water. But in water, it's like almost impossible to detect the front velocity. So what we can detect are things called group velocity and phase velocity. Those are more easily measured. And those are the things that are both about the same in water in the normal circumstances that we're used to, are about 75% of the speed of light through the air in the vacuum. So it's noticeably slower what you can measure through water.
I mean, how come it even slow? Like, is the light being absorbed by molecules of, because water is dense, for example? It makes sense. Like, if you have it go through water, is it getting absorbed by water molecules and then thrown out again? And
Well,
is that what's slowing it down?
that's one way to slow down light, but usually What happens is water molecules themselves, they jiggle around. They jiggle around mostly in the ultraviolet. The speed is equivalent to ultraviolet light. So if you put light through water, you cause the water molecules to start jiggling. And this jiggling then actually, since water is actually charged positive protons and negative electrons, that creates its own little kind of light. When you accelerate anything with charge, you get light. And this whole bundle then moves along at the center of the bundle at only 75% of the speed of the bundle that's outside of water. So it's the jiggling of the water molecules and the time it takes for, because the water molecules aren't all exactly in the line, they're like around the line. So the time it takes for information to go there and for this whole thing to go slows down the water. Well, the interesting thing is that as you go into the red, then you get less and less of that jiggling. And what you get is the photons then tend to, in the infrared, tend to make the water molecules spin around more. And as you go even more red, more red than infrared, you go into the microwave, you really get these water molecules spinning, so much so that you can heat your coffee. But the light that is the visible that we can see actually interacts with water relatively little. It's sort of in the valley between the blue stuff that causes it to jiggle and the red stuff that causes it to spin. There's a dip there, which is why we can see pretty far through water. But still, there is an interaction light is having through water, and that interaction is the reason why light moves slower through water than air or vacuum.
Now, hold on. There was something mentioned there, like
Mhm.
from what I'm understanding here, is like some light can beat other light
Yes.
in water.
So red light is going to go faster. If you have red light and blue light, the red light's going to go faster through water than blue light because the red light is interacting less with water than the blue. But if you go to vacuum, the red and the blue light, same as far as we can tell, exactly the same.
So is it does this keep going up the spectrum? Like if we go all the way to gamma rays, for example, would gamma rays get slowed down the most compared
Now,
to
crazy things happen. You get into different resonances and you get into absorption where you get into parts of the water can absorb photons of different energies. Crazy things happen. So you can't just linearly extrapolate it all the way to gamma ray.
okay.
Uh,
But
it's a
still,
clever
like
thought, but
depending on the frequency of the light, the
mhm,
electromagnetic
mhm.
radiation, is going to make some light move faster than other light through certain mediums,
Yes,
whether it's water or something else.
yes.
Interesting, interesting. Um, let's say I fire off some visible light in water, and then you're outside. You have a very, very powerful gun. You also bought it from Amazon,
Mhm,
and it can fire bullets at like 99% the speed of light. I mean, technically,
mhm,
you beat light there.
mhm.
Is that correct?
Yeah, so that's a famous thing that physicists use actually. So it's not only true, it's useful. So, although not with bullets, the guns that sell that shoot that fast are too expensive to be really useful for physics. But if yeah, so if you have a flashlight and you have a bullet that you fire into the water, at first the bullet, if it can go close to the speed of light in vacuum, will continue at moving close to the speed of light in vacuum, which is faster than the speed of light in water. So until the water just becomes too, which is like about a meter or so. But in that small space, the bullet is going to beat the photon until the bullet just slows down really small, really slow. But yeah, at first, a bullet can actually outrace light. But so another thing you can say is, okay, let's go smaller. Let's go a proton. So a proton also can move that starts entering water at the speed of light in vacuum can go for a longer way than a bullet than before slowing down. But there's even another particle called a muon that can be charged. And a muon can go a long way, can go the length of a swimming pool without really being attenuated very much. And so a muon can really outrace light for a long time. And that's why a lot of detectors in astrophysics right now look for muons because muons can do it. They can move that fast, and they leave something called Cherenkov radiation in their midst that tells us about their speed and about their direction and some really cool stuff. So this is not only true that you can move things faster than light can move through water for at least a while, but it's useful.
Interesting. So muons, they have mass, so
Yeah,
they can never reach the speed of light.
yeah.
But if you can accelerate them in a medium like water, they
There's
can beat the speed of light.
things
They
just
can beat
happen.
not the speed of light, they can beat light.
Yeah, muons are so light that things just happen in the atmosphere that cause them to go zipping at near light speed already. So we don't have to accelerate them. We just have to look for them and see them. Oh yeah, that one was moving, close to the speed of light for a long time before it slowed down, or it went all the way through the tank and we didn't see it slow down much.
Interesting. Now, the speed of light, like you keep mentioning, is the speed of light in a perfect vacuum,
Yes.
right? And from what I know, it is extremely difficult to have a perfect vacuum. There is always some particles, some atoms here and there. So,
True.
does light ever move at the speed of light in our universe?
Great question. So the answer is really no. So we've never found a really large place there's always something there, even interstellar space. You would worry about you can't breathe the little stuff that's there in interstellar space because it's so thin. And it's difficult to get vacuums here on Earth as to have as few particles to qualify as the vacuum in interstellar space. But still, out there in interstellar space, there's still your occasional particle. There's light coming in from different directions. There's particles going through in different directions. So yeah, there's never really a place that is completely empty for long of stuff. So the speed of light in vacuum is defined to be something that doesn't really exist. A pure vacuum is only a myth, a mythical being. It's an extreme that we've never gotten to. It's infinitely hard to create an infinite vacuum, an infinitely empty vacuum. So on Earth, we stop trying after a little bit. Okay, you have a vessel, do our best for a while to keep the number of particles in there as low as possible. But after a while, you just say, well, that's the best we're going to be able to do.
So theoretically, light should travel at the speed of light, but practically, this never happens.
Correct. It is a theoretical limit now. But it is the limit that appears in special relativity. And so when we do our calculations that distort time and space, as Einstein showed in special relativity, we use the theoretical limit. So it gets more.
So yeah, absolutely. Slow down a bit. So if light doesn't move at the speed of light, okay, what does? All right. If we look at, is there anything that moves at the speed of light? Practically, not theoretically, but practically.
So the best answer, I think, is no. There are other things that move very close. For instance, these muons, we usually see them moving very close to the speed of light. Things called neutrinos, they usually go very close to the speed of light. Gravitational radiation also moves very close to this maximum speed, but even gravitational radiation, it's an approximation that only exists if nothing's there. And then you get into the strange paradoxes. If nothing's there, how was it created? So you get into philosophical debates there. But yeah, if you had gravitational radiation in empty space, it should move at the maximum speed called speed of light, just like light does. But just like light always has something there, gravitational radiation actually does react to things in the space-time. And so even that does not move at exactly, only 99.99999% of the maximum speed. But there was a really interesting explosion that occurred, I don't know, maybe 10 years ago. And from this explosion, which was very far away, we got both light and gravitational radiation. And the really interesting thing was that it was hypothesized that they would move at the same speed. And so we saw the light, and this was from millions of light years away. And then we saw the gravitational radiation like 2 seconds later. So it traveled all the way across the universe, the light and the gravitational radiation pretty much together. Some people make a big deal of the fact that we saw the light first and the gravitational radiation second, because maybe it means that light is a little bit faster in gravitational radiation, but most scientists don't think that's a big deal. It just so happened that the light had a head start. So ready, set, go, light was already moving, gravitational radiation started a couple seconds later. So we, to the best that we can tell, they move at the same speed, which is the maximum speed called speed of light.
Uh, okay, so let's say, I don't know if you're a betting man or not, but let's say you're going to bet your life savings, and this is a very special race.
I need my wife's
Okay.
permission, but let's assume I have that for now.
Okay, let's say you have that permission, and there's going to be a race. What is the fastest thing in the universe practically? So we'll take a stretch of space, let's say between our galaxy to the Andromeda galaxy.
Mhm.
Okay, and we're going to let whatever these things go, right? They can go at any practical speeds, and you have to bet your life savings on one of them. What's going to win? Forget dark energy and warping of space. Just assume that it's just a straight line with just normal space.
Well, I would
Have a
think that it
think
would
about
be a
that.
tie, which means that it depends what happened at the starting line, which one got a little bit of a head start. So it's like having this big marathon race, and you're interested in who's going to win the marathon race, but really it only depends on what happened in that very fraction of a second when they all started out. You know, did someone get a first step? Did someone, whoever gets the first step, gravitational radiation and light, if they really started at exactly the same time, it would be a tie, and I would bet my life savings it would be a tie. Well, with permission, I would ask my wife to bet my life savings that it would be a tie. But so yes, but the things
So
like
it's
neutrinos, though, neutrinos might be a little bit slower. Muons, they would come in a little bit later because they would be traveling a little bit slower. Um, but between gravitational radiation and light, tie.
interesting. My I have also, can I, if I can I beat light? You know, so I was thinking of your example earlier of how water can slow down light. Is it possible to artificially create a medium that slows down light so much I can just walk past it?
Yes. So people debate as to what it exactly means you're slowing down light. So before we said that, well, when you can have atoms that absorb certain kinds of atoms will absorb the light, and if these atoms are prepared just right, they can absorb light and they can re-emit light that has like exactly the same properties later. And what modern science has been able to do is have it absorb, and then you can just sit there for as long as you want. Okay, it's absorbed it. This photon is sort of like frozen inside this molecule because it absorbed that light. And we know how to trigger it so that same light can then continue on later. So when that happens, then you could that doer of these molecules can just be sitting in the lab and you can walk by casually, you know, yawning, sit down for a while, stand up for a while, continue walking. You could beat that light, but that light would then be eventually, when you wanted, maybe could then be re-emitted and go later. But between the molecules, when it's emitted and then it may be absorbed by other molecules and then emitted, between there it moves at light speed. But we've learned to be able to capture light in such a way that we can re-emit it when we want to have all the same principles as when it was captured. So in a sense, you can now walk faster than light.
But this is not the same thing as being slowed down by water. This is a different mechanism that's
Yes, there's
slowing it
many
down simply
ways to
degree. Is
slow
that
down
correct?
light. One of them is absorption. One of them is causing it to jiggle. One is an interaction between the photon that causes the molecules to spin. And there are other ways too. And it's not my research specialty, so I'm sure we can find people in the comments below who have even other ways that I haven't thought of. And modern science, modern physics comes up with new ways all the time. But those are three big ones: absorption, jiggling because they're moving by, and causing it to spin.
Interesting. Um, I just I just had this thought
Mhm.
going back to the race earlier. All
Yeah.
right, now we're gonna have another race, but this time between different wavelengths of light.
Yes.
Okay, and we're gonna go from the Milky Way galaxy to the Andromeda galaxy. We have low energy radio, and then infrared,
Mhm.
visible light,
Yes.
um, gamma rays,
Gamma rays.
and then all of these photons start at the same time,
Yes.
right? And we fire them. You're gonna bet your life savings without your wife's permission.
Mm,
What's gonna happen?
reluctant there. So they would all they would all arrive. So through the vacuum of space, assuming it's a complete vacuum between here and the Andromeda Galaxy, it would be a complete tide. The red, the blue, the gamma rays, the microwaves, the radio waves, they would all get there at the same time. Now, because there is actually slight molecules here and there, it's actually very complicated. I don't even know the right answer to this. But depending on how the different wavelengths of light interact with the different molecules there, you might get ones that will slightly beat the others by very, very small fractions of a second. But if you're just getting down to, you know, thousandth of a second, you can't tell the difference. They all go the same, which is way different than if you tried to go through water. Vacuum is way different than water. So through vacuum, tie. All light pretty much takes the same. There's actually a name for that called the equivalence principle. Einstein was one of the people, actually, the equivalence principle dates back to Galileo and maybe even before. But Einstein played with the equivalence principle a lot and thought about it. And so it doesn't matter what energy the photon has, it always travels in special relativity at the same theoretical speed. Now, in water, not so much. Red light beats blue light. But out in space, tie.
Before I know you're very busy, and you know, I just want to ask you one last question, and then
Happy to
uh,
spend my time here.
you have PhD students to teach and papers to write. Um, if you had to share the most interesting fact about light, like out of all of this, like what's the most interesting thing to you? Have a think about that. Take some
Well,
time, drink some water.
oh, good question. Okay, I will drink water. So my mouth is a little dry.
Yeah.
But one of the things that got me into this is a relatively unknown type of things that occur with many photons called relativistic image doubling. So I've published some papers on this. So what happens is, in some circumstances, you can get a spot on the wall appear to break into two spots and move away without any lenses at all involved. And that only occurs, you don't see that when things only move slower than light. This is tied to the unusual world of superluminal, which means fast than light motion. So my students and I try to discover what exact geometries is it? Is this observer dependent, or does it happen just in reality, without any observers? And so we're finding that it happens even in reality without observers, but if observers see it, it's a little bit different. So you can take a single laser spot moving toward you. A laser spot moves not exactly toward you, but pretty much toward you at a speed faster than light. But what you don't see that though. What you see is when the laser spot is going toward you faster than light, you don't see anything because the light that leaves the laser spot hasn't gotten to you yet. So you see nothing. Then all of a sudden, you see what we call a spot pair creation event, and you see two spots created, and one moves toward you and one moves away from you. And so we study that because we think that if we can see this out in the universe, it's actually just been confirmed in the lab a few years ago. It's conceptually quite simple once you understand it. But if we could see this happening out in the universe, this could be an interesting thing that tells us about the universe, because when the spot that comes toward you faster than light, as it goes by you, its speed toward you must drop to below light speed. And it is exactly at that place where you see these two spots move off. So if we can see these spots being created out in the universe, we can know that there is an illumination front that's dropping exactly from moving faster than light to moving slower than light. And that gives us information we did not know before. And this is one of the things that just turned me on to this whole field. It's like, wow, who knows that? And I go outside and they don't even know shadows can move faster than light. So me and some colleagues and some of my students are now trying to study this and figure out not only what happens, because surprising things can happen, but is it useful? Can we use this to make 3D images? Can we use this to determine distance scales out in the universe? So it's a relatively young field right now, and the reason why it's coming to the fore right now is because you can do fast enough photography. You can do really fast photography. You can do, your phone can now determine times within a small fraction of a second. Whereas before, 50 years ago, it's just too fast. Maybe that happens, who knows, can't see it. But now with modern technology, we can see it and it might be really useful.
All right. So I just want to wish you and your students the bestest of luck.
Thanks.
And
good luck to you too. And it's been fun. Great questions. Been fun being on your show. And so I'm very happy to be here. Thank you very much for inviting me.
all right, fantastic. You have a conversation to have with your wife
Yes.
and Professor Robert Nemiroff from Michigan Tech. Thank you so much for coming.